In this video, we're going to find out what happens to the pyruvate that you made through glycolysis. And there are three main paths for pyruvate to take. One is the aerobic path, the one with oxygen, and that's the citric acid cycle, where you make NADH, carbon dioxide, and H2O, oxidative phosphorylation, you make ATPs, where you make your NAD+. We will cover the citric acid cycle in detail later on. Right now, we're going to focus on the anaerobic pathways though. One is to take pyruvate and convert it into lactate. This is called homolactic fermentation. And during this process, you take your NADH and convert it back into NAD+, so that can be used back in glycolysis, so you can continue glycolysis. The other path is done in yeast and other microorganisms. This is called alcohol fermentation. Same idea, where you take your NADH, make NAD+, so it can go back to glycolysis. But here you're making carbon dioxide and ethanol. Ethanol, we all know, is used in alcohol, and CO2 is important for making like bread rise. That's why it rises. So let's look at homolactic fermentation first. So let's say your muscles are working hard, so you need a lot of ATP. Well, and your oxygen's low, what are you going to do? You're going to make ATP via anaerobic glycolysis. The reason for this is that it's much faster than oxidative phosphorylation. True, you get more ATP through oxidative phosphorylation, but if your muscles are working, you don't have that time. You need ATP now, so you're going to create lactate. And the enzyme that's going to create lactate is called lactate dehydrogenase, LDH. Catalyzes the oxidation of NADH in pyruvate to yield NAD+ and lactate. And this is a reversible, freely reversible, so this can interchange. And they would readily equilibrate if given the chance. So the overall reaction for doing anaerobic glycolysis in mammals, for example, is glucose plus 2 ADP plus 2 inorganic phosphates go to 2 lactate plus 2 ATP plus 2 water and 2 acids. And lactate is what we're calling a dead end here, in that we can't get more energy out of it. It's done. So what we can do with it though is that we can export it out of the cell, or we can just convert it back to pyruvate when our energy needs aren't high, because again, this can do the reverse reaction. Note, in humans and mammals, multicellular mammals, this lactate is usually transported out of the cell, goes to the liver, and is actually remade back into glucose through gluconeogenesis, which we'll also talk about later on. And just so you know, lactate in your muscles does not actually cause muscle fatigue and soreness, even though everybody says it does. That's just not true. What is happening is why your muscles get fatigued and sore is because this acid is what is causing that soreness, not lactate itself. Now let's look at the yeast reaction. So yeast in anaerobic conditions will regenerate NAD+ through fermentation, which is creating ethanol. So you convert pyruvate to ethanol and carbon dioxide. And this is actually a two-step mechanism. The first step is to take pyruvate and do decarboxylation, which is what it sounds like, removing a CO2. And this is done by pyruvate decarboxylase. And the reason why mammals can't do fermentation, why if we're low in energy we just don't get drunk as well, is because we don't have pyruvate decarboxylase. We don't have this enzyme for this first step. So after this first step, you make this compound right here, and from that you're gonna reduce that to ethanol using NADH. So this is catalyzed by alcohol dehydrogenase, and you're also taking NADH and making it to NAD+. This NAD+ can go back into glycolysis and the GAP-DH reaction. For this reaction to work, the enzyme you need is thiamine pyrophosphate, TPP. Or it's not the enzyme, it's the cofactor rather. the cofactor of alcohol dehydrogenase. And, sorry, of pyruvate decarboxylase. And this is vitamin B1, thiamine, and it binds very tightly to your enzyme, but it is non-covalent binding. So this is all non-covalent interactions. So let's take a look at the mechanism for this decarboxylase reaction. So to have this reaction work, you need your TPP in the ylide form, and that means you have a dipolar carb anion. So here's your carb anion, and dipolar because you have two charges and it's polar, plus and a minus. So once you have the ylide form, your carbon will actually attack your pyruvate, your carbonyl carbon of your pyruvate, to form your one of your intermediate structures. From this, CO2 will be eliminated now, and you're going to get a resonance-stable carb anion. Acid will come and protonate your carb anion to make this intermediate. And once you have made this hydroxyethylamine pyrophosphate, then the acetaldehyde and your ylide will separate. You'll get your ylide back, and you're ready to do the next reaction as well. This reaction, although we're looking at it for yeast, is actually found in all organisms, a similar reaction, that is. And we cannot make TPP. Vertebrates cannot make TPP. We need to get it through our diet, vitamin B1. So B1 deficiency can cause problems. Most common is Burberry and Wernicke-Korsakoff syndrome, where you have neurological disturbances cause pain, paralysis, and atrophy. Okay, so we made our acetaldehyde in the last step. Now, our next thing we need to do is alcohol dehydrogenase to make ethanol. And the enzyme that's going to do this in yeast is called yeast alcohol dehydrogenase. Converts acetaldehyde to ethanol. YADH is a tetramer. That means it has 4 subunits. Each subunit has a zinc bound. And how this reaction works is that the zinc, that is non-covalently interacting with the cis molecules. You have your zinc, and it's acting with the oxygen of your carbonyl carbon. This is polarizing this bond even more, making this oxygen want to become negative. That's drawing electrons from this double bond that goes to this oxygen. Once the electrons are being drawn, that allows for an attack from NADH to give up its hydrogen, and you'll get NAD plus out in ethanol. Now, humans, in our liver, we have alcohol dehydrogenase, and what that will do is that it will take this ethanol and actually metabolize it anaerobically. So again, alcohol dehydrogenase in mammals and in yeast, both with no oxygen. It's very similar to YADH, except it's a dimer, and each dimer has 2 zinc being bound. All right, so let's look at the energy of these different fermentations. So to make lactic acid, delta G is -196. Fermentation, alcoholic fermentation is a little bit better, -235. Each of these processes, you can make roughly 2 ATP, because to make 1 ATP, delta G is usually like 61 kilojoules per mole. Now, these are standard conditions, these energies. Physiological conditions, these numbers change because all the concentrations change, but the reactions are roughly 50% effective, greater than 50% effective. The rest of this energy that is not being used to make ATP is lost as heat, so this reaction will then be irreversible. Like I said, you're only making 2 ATPs, so it's way less effective than oxidative methods, which make 32 ATPs, but it's 100 times faster. So by the time it would take for you to get 32 ATPs, you have made 200 ATPs. So yeah, you're burning more resources. It's not efficient, but it's fast. So when you're using your muscles and you're rapidly using ATP, all your ATP is going to be regenerated through making this lactate. That's it for this video. I will see you in the next video.